Hi, this is Wenbo from University of Oslo. We all know that body movement plays an important role in music performances and is widely being studied. However, how the expressive body movement and audio parameters change while trying to maintain consistent expressive intentions have not been answered. We designed a pilot experiment using motion capture and sound recording. Recorded a pianist played six excerpts on the three body movement conditions: deadpan, normal, and exaggerated, from easy to advanced difficulty level. We investigated the audio and body movement modifications from the performances. We found that the changes in expressive body movement affect the tempo and dynamics of the audio, which is also correlated to the difficulty of the music piece. Moreover, compared to exaggerated condition, restricted movements will affect the music more drastically. From the motion perspective, we found head and wrists move fastest during the performances, while the torso moved slowest. The motion velocity and the quantity of the motion of head is greatly affected on the different conditions. On the other hand, wrists is very stable during three conditions.
Hello everyone, my name is Miguel Cuadrado Sierra, and together with Jeremy Magoso and Jonas Brunskoy, I developed an audio-tactile art installation to enhance music experience of hearing impaired people, the so-called Kalimba bed. This installation consists of a wooden structure where people can lie on and feel a combined perception of sound and tactile stimuli. It was designed based on the local frequency selectivity of a system of cantilever beams with different widths, when a common frame is excited. Hence, different tactile stimuli would be mapped to specific positions of the body when lying on the structure. Our study includes a numerical simulation of the system of cantilevers, the building process of the prototype, a frequency response assessment, and a perceptual test with participants. We hope you like it. Bye!
Hello NordicSMC. This video is presented by Hong Zhao Guan, Zhao Yan, and Timothy Su. Our project is automatic piano fingerings estimation using recurrent neural networks. Deciding piano fingering is an essential skill for all pianists, from new piano students to concert pianists. Normally, piano teachers and music editors will manually label the fingerings on piano scores, which can be a tedious procedure. Therefore, in this study, we aim to address this problem using deep learning. That is, a trained model can help pianists estimate fingerings to piano music. In order to make a neural network understand the input data, we first designed a novel learning representation which converts each consecutive note pairs to computational vectors. In order to make a neural network understand the input data, we first designed a novel learning representation which converts each consecutive note pairs to computational vector. This four-dimensional vector accounts for the starting fingering, white notes, black notes, and note distance. Our neural network also accounts for not just previous notes, but also future notes in its decision making. Then we trained a multi-layer, many-to-one bidirectional LSTM network to learn piano fingering. This architecture mimics the fingering decision procedure of a pianist. To evaluate the results, we employ two metrics. The first one will measure the similarities between the ground truth fingerings and the estimated fingering. The second metric is newly proposed in this paper, and it evaluates the quality of the fingerings. The result will be labeled fingering with high playability on piano scores, and the generated fingerings also have a high match rate compared to the ground truth. Thank you, NordicSMC. Please have a look at our paper for more detailed results and conclusions. Thank you for your attention.
This is Joni Mock from the Department of Musicology at the University of Oslo. Today I'm presenting the paper entitled Designing the Structure of a Hybrid Conference. It is a report about setting up the hybrid conference for the Rhythm Production and Perception Workshop, the RPPW 2021. The setup was designed for participants from all over the world. The RPPW 2021 happened during the COVID-19 pandemic. It was a 4-day conference with around 300 attendees from more than 25 nations. The main challenges were conference scheduling because of the time zone differences and the participation methods because of the travel restriction. Here I will be presenting both the conceptual planning and the technical setup. In the conceptual planning section, it will include software, scheduling, and hybrid social interaction. And in the technical setup, it will include Zoom setup for streaming and the audio-visual. Finally, I'm presenting the responses from the participants, and we'll discuss about the process of designing the structure of a hybrid conference.
Our research explores modeling the sound of astronaut voice communications. Using a similar approach to Oksanen and Välimäki, we propose a practical signal processing method for emulating samples from NASA's Mercury 6 and Apollo 11 missions.
Roger, 0G, and I feel fine. Capsule is turning around.
It's one small step for man, one giant leap for mankind.
We first analyzed the reference sounds for key features to be included in the model. The model is composed of 4 signal processing stages. The first is a 2-band pre-filter, then a nonlinear wave shaping function, noise modulated by the speech envelope, continuous background noise, and finally a 3-band post-filter to band limit the signal. With manual tuning, we have found qualitative success emulating our chosen reference sounds.
That's one small step for man, one giant leap for mankind.
That's one small step for man, one giant leap for mankind.
In conclusion, this method for emulating astronaut communications is effective and practical for use in audio production applications. More generally, a 4-stage architecture is suitable for generating a variety of distortion audio effects.
Hello, I'm Simon and I'm presenting the paper Real-Time Implementation of a Physical Model of the Persian Santur. The santur is an old Persian instrument, consisting of 18 notes, each with 4 strings of the same tuning. The instrument is played using wooden hammers. It's no new practice to create digital emulation of acoustic instruments. Many different synthesis methods have been used for this purpose. The approach used in this paper is physical modeling and is used to model the physical behavior of the instrument. To model the strings, the equation of a damped stiff string is used. The body of the instrument was not modeled, but an impulse response was recorded. The equation of a damped stiff string was discretized using finite difference time domain methods and implemented using JUICE. The quality of the physical model was evaluated in a 2-fold listening experiment. Results from the evaluation showed that recordings of the real instrument was found to be more realistic than renderings from the physical model. Apart from this, multiple participants stated that it was difficult for them to tell which one was recorded and which one was synthesized. Conclusively, a real-time physical model of the Persian Santur was presented. The recordings were found to be more realistic than the renderings, but multiple steps, such as implementing a hammer model or recording a better impulse response, could increase the quality of the model. And now a very quick sound example.
Hi, I'm Pierre Potel and I present to you Solo Jam Island, a framework I designed along with Florent Winstra and Kirglet, which is used to study rhythm dynamics in multi-agent systems. The main goal of this framework is to study the role of migrating agents, i.e., musical agents navigating from one musical subgroups to the other, and the ways in which they influence the musical composition in those subgroups. These agents have the special task of incorporating rhythmic elements from the former group they were in to their new environment. The musical patterns played by the agents are represented as binary arrays, on which agent can apply genetic operations to make them evolve during the musical performance. They do so by the use of mutations, where an agent decides to add or remove a note at a given beat, or crossovers, where two agents mix their patterns together to create a new one. The system is thought as highly modular and flexible, allowing for many different scenario configurations. An open source Unity 3D implementation is provided online for experimentation.
Hi everyone, we're Emil and David, and we're media technology students from KTH. In our poster, we present the results of our study, sonification of hashtags using earcons based on the sound of vowels, that we co-authored together with our professor Roberto Bresin. We have investigated the ability of understanding and remembering sonified text messages using earcons by mapping vowels to their respective formant frequencies. The text data used were Twitter hashtags. The rhythm and notes of the earcon were also mapped to parameters of the hashtag. Here's a visualized example of the note mapping of the hashtag Stockholm. Participants in our study were able to recognize the earcon of a specific hashtag, but the effect of the enhanced vowel presence couldn't be proven. You're welcome over to our breakout room to find out more and to listen to the earcons. Here's a teaser of how Joe Biden sounds. Thank you from us here in
safely to the Earth.
Hello everyone, my name is Andrea Bolzoni and I present the paper Timbre, a timbre-based musical agent I wrote with Valentino Di Donato and Robin Laini. Timbre is a prototype of a musical agent that reacts to timbre gestures. We take the definition of musical agent from Tatar and Pasquier. Musical agents are artificial agents that tackle musical creative tasks, partially or completely. And we define a timbre gesture as a sonic as opposed to body gesture that mainly conveys artistic meaning through timbre rather than other sonic properties. Our dataset is structured as stimulus and reactions pairs, where we can have, for example, a guitar as input and a trumpet as output. We then train a model that can produce consistent reactions given, for example, a guitar as input. We developed two different architectures, one that uses MFCC and concatenative synthesis, and one that uses CQT both for analysis and resynthesis. We evaluated the system with 5 musicians that preferred the second version, and overall the system received a good evaluation. Thank you, and see you later in the breakout rooms for more information.